In this section we are going to continue looking at one-sided limits. Now in some previous sections we looked at the idea of one-sided limits to help us define what the concept of a limit was. So let's go ahead and look at this piecewise function that we see here, and we'll call this function f of x, and we'll start trying to answer some limit questions based on this picture. So basically we're finding the limits that we're going to be looking at graphically. So the first limit I would like to look at is the limit as x approaches 1, or actually let's do -1 from the right. Okay, so when we look at the limit as x approaches -1 from the right, basically what I do is I follow the graph. I have a big jump here, and as I approach from the right, as x goes toward -1, my y values are getting closer and closer to +1. And so my limit here as x approaches -1 from the right is +1. Let's go ahead and look at another limit. Let's look at the limit as x approaches -1 from the left of this function. Okay, well we have a little bit of a problem here. I want to approach -1 from the left, but there's nothing here. I can't approach it. I can't get to the value of -1 from the left. So from the left, this limit does not exist. So if you think about this, these are not equal. +1 and d and e are not equal. Therefore, the limit as x approaches -1 in general of the function f of x does not exist either. So what I have here is only the one-sided or the right limit existing. Okay, let's go ahead and look at another problem. So for our next one, let's go ahead and look at the limit as x approaches +1. And we're going to approach from both directions. So let's go ahead and look at approaching +1 from the left of this function. And we'll also look at the limit as x approaches +1 from the right of this function f of x. Okay, let's go ahead and approach 1 from the left. So we jump on the curve and we follow the curve, and we can see as x gets closer and closer to 1, my y values get closer and closer to 2. Now, you might say, well wait, that's a hollow point, so there cannot be a limit there. But remember, I'm approaching 1, I never quite equal 1. I get closer and closer, but I never equal that particular value. So the hollow point doesn't end up mattering here. So the limit as x approaches 1 from the left is 2. Let's go ahead and look at the limit as x approaches 1 from the right. As we approach 1 from the right, we can see that we kind of have a constant function here, and my limiting value, or my y value, is a +1. So the limit as x approaches 1 from the right is a +1. These are not equal either. Therefore, the limit as x approaches 1 of the function f of x does not exist. D and e does not exist because the limit from the right and the limit from the left do not agree. We can see also that there's this big gap, or this big jump from the two directions. Okay, let's go ahead and look at another limit. For this next limit, let's go ahead and look at approaching +2 from the left of f of x, and let's look at the limit as x approaches +2 from the right of f of x. Okay, well here's my value of 2. I want to approach 2 from the left, and we can see as I approach 2 from the left, my y value stays very steady and gets closer and closer. As I get closer and closer to 2, it gets closer and closer to 1. And it actually is a constant value of 1 here, but I do have a hollow point. I wouldn't expect as I got closer and closer to make this big jump to 2. So as I'm finding the limit, as it turns out, it makes no difference whatsoever that this is the filled point up here and this is the hollow point down here. So the limit as x approaches 2 from the left is 1. And by the same reasoning, as I approach 2 from the right, my limiting value is 1 as well. Well, finally, these are equal. Therefore, the overall limit as x approaches 2 of f of x is equal to 1, because the limit from the right and the limit from the left agree. Now, as a quick side note, I want you to remember that when I'm taking one-sided limits basically have all the same property of two-sided limits. So these properties would include things like the limit of a constant is a constant. The limit of a sum is the sum of the limits. The limit of a product is the product of the limits. The limits of a quotient is the quotient of the limits. And I guess the constant multiplier rule, if I have a limit of a constant times something, I can pull that constant out front. So all the one-sided limits have all of the exact same properties of the two-sided limits that we've worked with before. I would like to talk about one-sided limits in the context of the plugging and chugging idea, meaning plugging in a value and seeing what we get back out, because sometimes they can be a little bit misleading. So let's go ahead and look at an example of the limit as x approaches 0 from the right of the function the square root of x. Now typically what we would do is we would take 0 and plug it directly in and see what we got back out. Well, if we plug 0 directly in, square root of 0 is 0. So it looks like it should be 0, but I want to verify this graphically. So we need to know something a little bit about the graph of the square root of x. Well, let's plot some points to figure this out. You can also grab Maple. If I plug in a 0, the square root of 0 is 0. If I plug in a 1, the square root of 1 is 1. So now, right now, it looks like a line just kind of bisecting this first quadrant. But really what happens if we go out here to, let's say, 4, the square root of 4 is 2. So we can see that it's actually kind of plateauing out. So this is what the graph of the square root of x looks like. So we can see as we approach 0 from the right that my limiting value or my y value is going towards 0. So that makes perfect sense. Now this is the rub. The limit as x approaches 0 from the left, I have a problem. Now again, typically we would take this and just kind of mindlessly plug it in and see what we get back out, and we get a 0 again. However, we can see on this particular graph I can't approach 0 from the left, so I have a little bit of a problem. This is actually not correct, and the graph verifies that. Plugging directly in, I have a little bit of an issue when I just plug in and I don't check and have a look at what the graph is. And I usually only need to worry about this when I have some sort of a domain restriction. Now what ends up happening here is the domain of this function, x values have to be greater than or equal to 0. So the domain here, x is greater than or equal to 0, because I can only take the square root of 0 toward positive infinity of a positive number. I cannot take the square root of a negative number, so I cannot approach 0 from the left. So I need to keep in mind that domain issue. So this limit actually equals does not exist, or DNE. So you have to be careful about plugging directly in when you have things like a restriction in a domain, or maybe a fraction that can be have a 0 in the denominator, or might have a radical in the denominator that can equal 0 and cause some problems. The next function that I want to look at has some other interesting characteristics that we haven't really seen yet in any other graphs. Well, let's look at the limit as x approaches 0 of the sine of 1 over x. Now again, let's go ahead and plug 0 directly in, and I get the sine of 1 over 0. Well, we can see right away that that's a little bit of a problem. But I would like to figure out what is the limit as x approaches 0 of just this argument. So let's go ahead and just consider this argument. Well, the graph of 1 over x looks something like this in the first and third quadrants, and this is a graph that you should know because it comes up so often. So again, this is the graph of f of x equals 1 over x. And if I look at this, and I'm talking about the limit, I can see as I approach 0 from the right, I'm going toward positive infinity. As I approach 0 from the left, it's going toward negative infinity. So let's go ahead and look at this in terms of one-sided limits. Let's break this up. Let's look at this as the limit as x approaches 0 from the left of the sine of 1 over x. And as we approach 0 from the left, I can see that this is actually going toward negative infinity. So again, as we approach 0 from the left, this piece is going toward negative infinity. So really, I'm kind of thinking like this, and it's actually not accurate to write it as a sine of negative infinity, but the sine approaching negative infinity. I have a little bit of a problem, because with the sine curve, and again the sine curve continues on forever in either direction. The sine of 0 is 0, the sine of pi over 2 is 1, so that kind of gives us our start here. The sine curve continues on in this periodic nature both toward positive and negative infinity. So the sign of negative infinity doesn't rest on a particular value. It's actually bouncing back and forth between -1 and +1, so this limit does not exist. Now if we take the limit as x approaches 0 from the right, same argument. As we approach 0 from the right over here, this is going toward positive infinity. So this is the sign of positive infinity. Same thing. What ends up happening here is this function, as we go toward positive infinity, is oscillating back and forth between -1 and +1. So the sign of infinity is not, going toward a particular value. It's bouncing back and forth between two predictable values, but it's not resting on one value. So this limit does not exist either. So the limit from the right and left, neither one exists. So therefore, I would have to say this overall limit as x approaches 0 of the sign of 1 over x does not exist. So it does not exist as our answer. But I would like to plot this in Maple to have a little bit of a graphical look at this. Now this is a big problem. We've looked at the graph of 1 over x, and we've also looked at the graph of the sine of x. And now we're going to look at the graph of the sine of 1 over x. Okay, so let's grab Maple and see what we get. So first of all, something to keep in mind, when we're working in Maple, Maple is in radian mode. So here's the sine of 1 over x. Don't forget your semicolon. Right click, I'm going to go to plots, 2D plots. Ooh, that's kind of an interesting graph. It looks like to me as we approach 0, this thing is kind of going towards 0 right in here. But actually what's happening is this graph, this function, is oscillating back and forth very, very quickly between -1 and +1. We can see here's the -1 and here's the +1. And as we get towards 0, it's kind of bouncing back and forth, faster and faster, and it's not actually going toward a particular value right here at the origin. In fact, it skips right over the top of the origin like a hollow point because we already know 1 over 0 is undefined. So if we want to get a little bit better look at this, and again remember we're in radians here, let's change the horizontal axis scale to kind of zoom in. So I'd like to go from -1 to +1. Now this is 1 radian, -1 to +1 radian. Now in this view, I can kind of see it start spreading out a little bit because I'm zooming in on it, but for the most part I kind of still have this big solid block down the middle. So let's try one more. Let's go -0.1 to +0.1. Ooh, wow, look at this. We can see that it's bouncing back and forth, but remember what Maple does is it just plays connect the dots, and so it's just connecting the dots through here. It doesn't realize there's a hollow point here. So here's a nice little graph, and of course this solid mass in the middle, what's happening is I have that oscillating function. It's bouncing back and back very, very fast. But we'll go ahead and stick that into our lecture so we can get a good look at what that is. So when we look at that particular graph, we can see that D and E makes sense. Because of that oscillating behavior, it makes sense to see that that limit does not exist. So again, another verification. We looked at this limit from the right, limit from the left, but this also shows that the graph of the sine of 1 over x as x approaches 0 does not exist. The limit does not exist. Now, because we're working with trig functions, I would like you to recall from one of the first lectures that we had on limits an interesting theorem. So recall from a previous lecture the limit as theta approaches 0, this is a Greek letter theta, of the sine of theta over theta. Now a couple quick points. You have to have arguments around your trig functions, even if it's a single variable. Put them in. It'll cause you a lot less grief a little bit later on when we're talking about the derivatives and integrals of functions. So always put parentheses around the arguments of your trig functions. So when we worked with this before, as a quick review, we plug directly in, and I have sine of 0 over 0. Sine of 0 radians is 0. 0 over 0 is indeterminate. Indeterminate means to do more work. Okay, well, the more work that we decided that we could do for this is we could look at this graphically. Now again, you can create a table, approach from either side, plug in values, but we're going to take a quick look at this graphically, kind of just to remind us what's going on here. So again, I'm looking at the sine of theta over theta. Now when you open up Maple, I don't think it's a grand idea to use thetas instead of x's. So I'm just going to go ahead and use x, just because they're easier to input. So I have the sine of x over x. I'm going to right click, plots, 2D plot, and I can also write a plot command, but this gives us a good idea of what's going on here. Now I'm going to go a little bit beyond so I can make sure that that's crossing right at 1 for our maximum value. So I'm going to go up here to 1.2. Again, I encourage you to make sure that you know how to use Maple, because it really is a good thing to use. And here we have the graph of the sine of theta over theta. Well, remember, this graph has a shortcoming in the fact that it should have a hollow point here, because theta, when theta is 0, I have 0 in the denominator. So again, I have a little bit of a problem there. So this is a graph of sine theta over theta, but I can see that the limit as theta approaches 0 from the left of sine theta over theta is equal to 1, and the limit as theta approaches 0 from the right of sine theta over theta is equal to 1. And because these are equal, the overall limit as theta approaches 0 of sine theta over theta equals 1 as well. So the limit as theta approaches 0 of sine theta over theta equals 1. Now this is important to remember. It's a theorem that shows up often enough that you want to keep it on a note card, a bookmark in your textbook, at the top of your paper, in the back of your tablet, somewhere that's easy to access so you can always look back to it, because we use it to solve other theorems other limits as well. And it's a theorem in our calc book as well. Let's go ahead and look at another common limit that we also like to work with. Let's look at the limit as theta approaches 0 of another function involving trigonometry, and this is the cosine of theta minus 1 all over theta. And again, I want you to be really clear on this. The argument of the cosine function is theta. It's not theta minus 1, so you should always put your argument in parentheses. Now if we plug directly in, I get the cosine of 0 minus 1 all over 0. The cosine of 0 radians is 1. So I'm left with 0 over 0, which is indeterminate. Indeterminate means to do more work. And again, we usually abbreviate that, DMW, do more work. Well, the more work that we could do here is we could look at this graphically, numerically, or algebraically. Well, we're going to look at this one algebraically, and actually we're going to be using some nice little trig identities that you probably would recall. I don't expect you to have these memorized, but you probably will recall how to work with these identities. And then we'll also work with this graphically. Now numerically is when we'd actually go through and create a table. So let's go ahead and look at this algebraically. Okay, so in order to look at this algebraically, we need to use a trig identity. And this little trig identity says that the cosine of theta is equal to 1 minus 2 sine squared of theta over 2. Okay, so that we're using this identity in order to establish or prove this particular limit. So let's go ahead and get started. The limit as theta approaches 0 of the cosine of theta minus 1 all over theta. So what we're going to do is, since we have this new definition of cosine, we're going to go ahead and plug in this binomial trigonometric identity in its place. So what this is going to look like is the limit as theta approaches 0 of 1 minus 2 sine squared theta over 2 minus 1. Now where did the minus 1 come from? The minus 1 came from right here. So here I have a minus 1, and here it appears over here as well. And this is all over theta. Okay, well I can see pretty clearly here that the 1 and the minus 1 cancel, and I'm left with the limit as theta approaches 0 of minus 2 sine squared theta over 2 all over theta. Okay, now we need to talk about thoughts for our next step. If we take this limit as is right now and we go ahead and plug in 0, I would get the sine squared of 0. Okay, sine is 0, radians is 0. So I'd still get 0 over 0, which is indeterminate, do more work. So I need to figure out what that more work is. And I think what we're going to do is we're going to keep trying to rewrite this. Now if we look at this closely, this kind of looks like it has some of the nice components of that sine theta over theta, or close to it. So what we're going to do is we're going to make a quick little substitution here. So let's go ahead and look at the substitution. And for our particular case, let's go ahead and let we'll let u equal theta over 2. Okay, so if we do that, let's go ahead and rewrite our next step. We'd have the limit here then as theta approaches 0, and I'm going to pull the negative 2 out front, sine squared theta over 2. Okay, but we just said theta over 2 is equal to u, so I'll have a u here. And then this theta right here, I could actually divide by 2 as well. So let's go ahead and look at a couple things here. I'm going to make another substitution just like we have here. And now remember, what ended up happening here is I divided the denominator by 2. Now if you divide the denominator by 2, you're going to see that the overall effect, you divide by a fraction, you multiply by a reciprocal, is actually multiplying by 2. So another way that we could look at that would be to say, well, I also have to have a 2 here because 2 divided by 2 is 1. So the overall effect here was just multiplying by 1. Now again, I'm looking for theta over 2. Well, if theta approaches 0, theta over 2 also approaches 0. So let's go ahead and have a look here. Here I have my negative 2, limit as theta over 2, which is u, approaches 0, of sine squared of u. Well, let's look to see what we have here. Here I have this theta over 2, which is u, and then I actually have this other 2 that's running around as well. Well, here I have a 2 in the numerator and a 2 in the denominator, so they cancel, and I'm left with negative limit as u goes to 0 of the sine squared of u over u. Okay, well this is looking pretty good because again we have that little theorem we can use. Negative limit as u approaches 0. I could rewrite this as the sine of u over u times the sine of u. Now the limit of a product is the product of the limits, so I'm going to rewrite this negative limit u approaches 0 sine of u over u times the limit as u approaches 0 of the sine of u. So the limit of a product is the product of the limits. Now for this piece right here, I know from up above that we just showed that the sine of theta over theta is 1. So the sine of u over u is 1 as long as u approaches 0. So for here I'm left with a negative sign. This value goes to 1. And then this piece, the limit as u goes to 0 of the sine of u, that's just the sine of 0. And the sine of 0 radians, of course, is 0. So this is going towards 0. So after all this work to establish this, I finally figured out that the limit as theta approaches 0 of the cosine of theta minus 1 all over theta equals 0. So that's what I came up with here. Okay, well I would like to check this graphically as well. So let's go ahead and make a little bit of room here and let's check this graphically. Now I really hope that this graph verifies this. So cosine of theta minus 1 all over theta. So cosine of theta, and I'm just going to use x, minus 1. Whoops, I better put parentheses because I have a binomial in the numerator, all over theta or x. So there's the function I'm looking at. I want to plot it, and I could also use a plot command, and there's my graph. So let's go ahead and paste this back in and have a look. Well, entirely too large. Let's fix that. Okay, now that we have it fixed, we can look at this and we can say, okay, the limit from the left is 0, the limit from the right is 0, therefore the overall limit of the cosine of theta minus 1 over theta is 0. So this graph verifies that. Now another interesting thing that Maple will do is it'll find these limits for you. So if you go under here under your expressions palette on the left, you can see that we have limit notation. Well, what ends up happening here is I can just input my function. Well, I already input it up here, so let's go grab it. Let's just highlight it from here because I knew it worked, and we just replaced the f with our function, Control V, and x is approaching in this particular case 0, so I put a 0 here. Got to get rid of the a though and approach 0. And this tells me that the limit is 0 as well. Okay, I'm going to go ahead and snip this right into our lecture so you can see what the command looks like in order to figure that out. And we can see here that we verified this several different ways. The limit of this function is 0. We've shown it algebraically, we've shown it graphically, we could use this numerically if we wanted to create a table, and I've also verified this with Maple. So I have two very important theorems or limits that I want to keep in mind in order to solve other limits as well. So I have two formulas to remember. And remember, you're going to be using these a lot, so put them on a note card, put them somewhere where you remember these. So the first one was the limit as theta approaches 0, sine theta, parentheses around the arguments of your trig function, equals 1. And the other one is the limit as theta approaches 0 of the cosine of theta minus 1 all over theta equals 0. So this is really important. You want to remember these. Now on a test or a quiz, you need to be able to recall these and use these. So again, you're going to use them often enough during your homework that you should be able to commit them to memory just because you've used them so much. But again, when you study for your first exam, you need to know these. Now, where are we going to use these two formulas? Well, let's go ahead and look at an example where I'm trying to find the limit as x approaches 0 of sine of 2x over x. Okay, well, the first thing we usually do is plug directly in. So if we plug directly in, I end up with the sine of 0 over 0. The sine of 0 radians is 0. 0 over 0 is indeterminate. And indeterminate means to do more work. DMW. Well, the more work we can do here is algebra. What I can do is I can rewrite this. Limit as x approaches 0, the sine of 2x all over 2x. So I want a 2 here in the denominator in order for these to match up, because the argument and the denominator have to be the same in order to use this little theorem right here. Well, if you divide by 2, you have to multiply by 2. Now also, because I want my argument to be 2x, the argument has to go towards 0. So I can see over here, if x approaches 0, 2x approaches 0 as well. So working on this constant, I can pull out front. Now let's do a substitution. Let's let u equal 2x. So I have the limit as u approaches 0 now of the sine of u over u. In this whole piece right here, this equals 1 by this formula up here that we need to remember. So I get 2 times 1, 2 coming from the coefficient out front, equals 2. So the limit as x approaches 0 of sine of 2x all over x is 2. And again, we have some work to be shown to come up with that. And we could also look at this with Maple. We could look at it graphically. And then I could also put in a Maple command to find the limit like we did in the last example. Okay, let's go ahead and look at another example. Let's take the limit. Oh, trig is so fun. Let's take the limit as t approaches 0 of the tangent of t times secant of 3t, and again, parentheses around the arguments of your trig functions here are particularly crucial, all over 5t. Okay, the first thing you do is you plug directly in and see what we have. That would be the tangent of 0 times the secant of 0 all over 0. Well, the tangent of 0 radians is 0. The secant is 1 over cosine. The cosine of 0 is 1. So this is 0 times 1 over 0. 0 over 0 is indeterminate. And indeterminate means to do more work. Okay, well, the more work that we can do is we can start rewriting this. So the limit as t approaches 0, tangent is sine over cosine. Secant is 1 over cosine, but remember the argument has to be 3t here. And this is all over 5t. Okay, so let's see if we can rearrange this a little bit. This is the limit as t approaches 0 of the sine of t. Okay, I'm going to move these cosines out. 1 over cosine t, 1 over cosine of 3t. So again, I just took this big numerator right here, this layered numerator, and I rewrote it. Now, let's have a quick look. This is actually 5t over 1. So when you divide by the fraction, you're actually multiplying by the reciprocal, and this flips to put 5t right into this denominator. So again, if you're not sure about this, remember this is actually over 1. When you divide by a fraction, you multiply by the reciprocal, and the reciprocal is 1 over 5t. Well, this piece right here is remarkably similar to the problem that we just did up here. So we can see here that I want to rewrite this a couple different ways. First of all, I can't put a 5 in here. I can't put a 5 in the argument of a trig function. You can't mess with the argument of a trig function like that. You can usually halve it or double it using some trigonometric identities like double and half angle formulas, but the easiest thing to do here would just be to pull that 5 out front. When you pull that 5 out front, you actually have a 1/5 out front. The limit as t approaches 0 of the sine of t over t times 1 over the cosine of t times 1 over the cosine of 3t. So let's have a look. 1/5. Now this piece right here is that theorem, that formula all over again. This equals 1 by that formula. So I have 1/5 times 1. Now for this next piece, the cosine of 0 is 1. 0 radians is 1. So this leaves me with 1 over 1. And for the next piece, the same thing. As t goes to 0, this argument goes to 0. The cosine of 0 is 1. And I'm left with here 1/5 times 1 is 1/5. So you're going to have to get pretty sharp with your algebra skills, because we're going to assume that you know how to work with your trig functions, you know your trigonometric identities, you can rewrite tangent as sine over cosine, you can rewrite secant as 1 over cosine, and you can use that with algebra in order to solve a problem like this. Now, let's go ahead and take a second to check this in Maple. Okay, so well, let's use the limit function. It's going to graph it, but let's use the limit function. Okay, so for the limit function, first of all, we have to put a big function in here. I don't really like that. What I'm going to do is I'm going to input the function first to have a look at it to make sure it's what I expect it to be, and then kind of work from there. So we have the tangent of x. Now remember, you have to put in the asterisk in Maple. So if we're going to take tangent of x times the secant of 3x, here we go, has to be 3 times x. Now all of this is divided by, in parentheses, 5x. Has to be 5 times x. Let's have a look at this to see if it's what we think it should be. Yep, tangent of x times the secant of 3x all over 5x, and it pulled the 1/5 out front, but that's good. So again, we have to be careful here. You have to make sure you have everything in parentheses. If you had decided to put the numerator in parentheses, it wouldn't have hurt anything. Still an equivalent value. So we know this is the right function. So now when we put it in our limit, we don't have to worry about how it looks this way, because we know when we see it written out in a vertical fraction form it's correct. Now we're taking the limit here as x goes to 0. Now if you choose to use another variable like t, just make sure that you put as t goes to 0. So let's go ahead and enter and see what happens. We get 1/5, and that's exactly what our solution was as well. Okay, so these are actually kind of a little bit backward. I should have input the function first and then plugged into the tangent, but we can see here that it agrees with my solution. So I encourage you to use Maple a lot to check those types of solutions. Not to do the work, but to check the work. And again, we can see here that the solution is 1/5. Okay, I think that gives us a pretty good talk about left limits, right limits, one-sided limits, and also the idea and concept of overall limits. And we also introduced a lot of trigonometry, so that's very exciting.